Hi everyone, today I'm sharing with you our recent study on rule choice modeling, and the topic is about combining the data-driven methods and machine learning techniques in choice set generation and model estimation. This research was conducted under the supervision of Professor Shlomo Bekhor, and I would like to thank him for his guidance and help during this study as well. So let's begin with what's rule choice modeling. Basically, the rule choice modeling answers the following question. What could be the alternatives that are considered by the driver, and which alternative is likely to be chosen by the driver? On the right-hand side, you can see an illustration of what is the choice set and which alternative was chosen. And notice that these two alternatives are described with some characteristics, like using route number 6 is the fastest route, but you need to pay the toll, while using route number 2 is a congested route. However, in reality, rule choice modeling is a non-trivial task since it involves the determination of a relevant choice set, which is typically very difficult to observe, unlike what we can simply see here. And moreover, the specification of the utility functions and the estimation application of the rule choice models are also very challenging. Our research deals with these two problems. So currently, there are three approaches that tackle the rule choice generation problem: explicit, implicit, and data-driven methods. All of them has pros and cons, as you can see here. Our proposed data-driven method not only is computationally efficient, but also able to include alternative routes that are considered but not chosen in choice set. So about the rule choice models. Traditional discrete rule choice models can provide rich behavioral interpretations, but specifying an appropriate utility function is difficult. Machine learning models have proven its robust prediction ability, but with relatively poor ability for behavioral interpretation. Our proposed model is one of the few studies that combines machine learning techniques with traditional discrete choice models, which not only provide rich behavioral interpretations, but also high prediction accuracy. Our proposed methodology is a six-step procedure for choice set generation and rule choice modeling. The data preparation step extracts rule attributes from observations and convert them to be non-volatile rule characteristic attributes. For example, we can see here like route directness, percentage of delay, and you can see a list of this normalized route characteristic attributes. These attributes are expected to capture the overall characteristic regardless of the treatment and serve as input to the clustering step. So unlike previous studies in which clustering is applied to identify the route choice set for each origin-destination pair, our clustering step identifies observed routes with common characteristics. More of the cluster labels can also provide behavioral interpretations to a cluster. The lower figure provides a visualization for different clusters. After distinguished route characteristic clusters, we're interested to find features that describe such characteristics. In the feature selection step, we utilize the cluster label from the last step and all the available attributes to train the random forest classifier. The random forest provides feature importance as criteria to select features with significant explanatory power. As you can see in the figure, with only 24 features, which are in green, out of the 50 features, we're able to contain more than 90% of all the information represented by the features. As you will see, the result of random forest reduces the risk of overfitting and improves the model estimation accuracy and efficiency. So based on the selected features provided by the random forest, we'll apply the data-driven alternative sampling method to generate the choice set. Our proposed data-driven alternative sampling approach is inspired by the labeling method. However, our method does not require artificially defining the labels and explicitly searching for alternative routes in the network. Instead, we sample the normalized route characteristic attributes to describe the alternative routes. Our approach tries to capture individuals' interpretation on different routes by differentiating routes with their characteristics rather than the explicit attribute values. The MI method aims to find statistically significant explanatory variables and obtain a model with high goodness of fit and prediction power. The overall procedure is shown here. The MI method can be seen as a two-level backward elimination procedure. The upper level checks selected features from less important to most important one by one and eliminates insignificant features. The lower level checks for coefficient correlation of all the coefficients of a checking feature. It iteratively combines the two highly correlated coefficients and then estimate a new model. In order to validate the model prediction power, the data set is randomly split into a training set and a test set for independent prediction. And the prediction accuracy is measured using S1 score. Here we show the result of clustering observation based on the normalized route heuristic attribute. This step not only provides each route with a cluster label, but also provides us behavioral interpretations to route heuristic labels. We infer the cluster labels by comparing the mean values of the attributes to the overall mean. As you can see here, the behavioral interpretation of the clusters are pretty clear and meaningful, which is critical to the success of the proposed data-driven method. Here we show the fitted distribution of each route heuristic attribute for all the clusters. The different distribution of the route heuristic attributes among clusters also justify that the previous clustering step can generate distinguished clusters. We compare the prediction accuracy of the estimated MI models, traditional discrete choice models, and machine learning models in the same test subset. Among all the models, the random forest model with 50 features outperformed all other models in terms of prediction accuracy, but the final model provides the best prediction accuracy, 73% among all the 4 discrete choice models. Note that with similarly defined utility functions, the conventional model exhibits much lower prediction accuracy in comparison to MI.
1 minute, please.
Runtime performance results are also confirmed that the random forest is able to remove unimportant features and improve the runtime performance of the MI models. So to conclude, the success of the proposed method is highly dependent on the clustering step. Without properly defining a cluster attributes, it's not possible to generate a high-quality cluster. As shown in the results with proposed data-driven methods, produces a discrete choice model with high prediction accuracy by combining the machine learning techniques with discrete choice models. In this study, it applied the method for simple MNL models, but the methodology proposed can accommodate more complex model forms. In future works, the more sophisticated root choice model that can scale root overlapping will be incorporated to the proposed method. Thank you, and if you are interested in more detail, refer you to the full paper.